Hi, everyone. I'm Hui Tang. Today I will talk about my recent work. These are the contents I will present. As we know, the great success of deep learning relies on massive labeled data. Many tasks lack labeled data. How to address this problem? We can tackle it with data-efficient learning, such as transfer learning, unsupervised domain adaptation, and so on. In transfer learning, if the new task lacks high-quality training data, the knowledge from the previous task can be transferred to the new task. We focus on the typical scenario of domain adaptation, transfer knowledge of synthetic data to help classify real data. When the source and target domains have different distributions but share the label space, the transfer learning problem is equivalent to the domain adaptation problem. We consider the most practical setting, unsupervised domain adaptation, where target samples are all unlabeled. Given labeled data on the source domain, UDA is to predict class labels for unlabeled data sampled from the target domain by learning a classification model on both labeled source data and unlabeled target data. As for synthetic datasets, VisDA 2017 is the first large-scale cross-domain object classification dataset tailored for domain adaptation from simulation to reality. In VisDA 2017, synthetic data are generated by 3D rendering and domain randomization. As for pre-training and then fine-tuning, there are many works on large-scale real data pre-training, for example, utilizing JFT 300 million to study the influence of pre-training on downstream vision tasks. The mainstream UDO approaches take the transfer strategy of learning aligned feature representations across domains. For example, DANN leverages a domain adversarial task to align the source and target domains as a whole, such that class labels can be transferred from the source domain to the unlabeled target one. DANN only achieves domain-level feature alignment. MCD uses individual task classifiers for the two domains to detect non-discriminative features by maximizing the classifier discrepancy and reversely learn a discriminative feature extractor by minimizing the classifier discrepancy. MCD achieves the finer class-level feature alignment. This figure shows sample images from the training and validation domains of VisDA 2017 and our synthesized data. It demonstrates that we vary the values of much more image variation factors, leading to more realistic and diverse samples. There exist basic and important problems in the context of image classification: lack of comprehensive synthetic data research, insufficient exploration of synthetic to real transfer. To address these problems, we use a 3D rendering engine to build large-scale synthetic datasets, theoretically infinite, and do a comprehensive study on supervised learning and downstream transferring. We aim to explore the answers to these interesting problems, which in fact are the main contributions of our empirical studies in this paper. Existing works verify classical theories and reveal new findings on real data. However, the process of acquiring real data cannot be controlled, the annotation accuracy cannot be guaranteed, and there may be duplicate images in the training set and test set, which leads to the fact that the training set and test set are no longer independent and identically distributed, IID. In this paper, 3D rendering and domain randomization are used to generate synthetic data, whose training set and test set are strictly IID under this ideal experimental condition. The classical learning insights such as PAC generalization and variance bias trade-off are verified. In particular, a new perspective of shortcut learning is validated. Randomization of training image variation factors can prevent models from learning shortcut solutions that rely on contextual cues in the background. This paper also explores the influence of network structures, model capacity, training data volume, and data augmentation on model generalization. Among the experiments, the key design is to compare the traditional fixed dataset periodic training with the new strategy of training on non-repetitive samples. These are the training data, test data, and network structures for the empirical study of bare supervised learning. For the empirical study on fixed dataset periodic training versus training on non-repetitive samples, we find that, with strong data augmentation, the test results on synthetic data without background are good enough to show that the synthetically trained models do not learn shortcut solutions relying on context clues. For the empirical study on evaluating various network architectures, we find that, in IID tests, VIT performs surprisingly poorly whatever the data augmentation is, and even the triple number of training epochs does not improve much. For the empirical study on impact of model capacity and impact of training data quantity, we find that there is always a bottleneck from synthetic data to OOD, real data, where increasing data size and model capacity brings no more benefits. and DA to bridge the distribution gap is indispensable except for evolving the image generation pipeline. For the empirical study on impact of data augmentations, we find that, for the data unrepeatable training, IID and OOD generalizations are some type of zero-sum game with respect to the strength of data augmentation. In addition, this paper explores how variation factors of an image affect the model generalization, such as object scale, material texture, illumination, camera viewpoint, and background. We find that different rendering variation factors and even their different values have uneven importance to model generalization. The observations also stress the underexplored topic of data generation, auto-simulate, namely weighted rendering. In previous experiments, we observed that bare supervised learning on synthetic data results in poor performance in OOD, real tests, and pre-training and then domain adaptation can improve. However, to our knowledge, there is little research exploring the effects of pre-training on DA. We thus study how different pre-training schemes including synthetic data pre-training affect the practical, large-scale synthetic to real classification adaptation. These are the pre-training data and downstream task in the empirical study of exploring pre-training for domain adaptation. For the empirical study on the importance of pre-training for DA, we find that DA fails without pre-training. For the empirical study on effects of different pre-training schemes, we find that different DA methods exhibit different relative advantages under different pre-training data. The reliability of existing DA method evaluation criteria is unguaranteed. For the empirical study on synthetic data pre-training versus real data pre-training, we find that synthetic data pre-training is comparable to or better than real data pre-training. Synthetic data pre-training is promising. This figure also verifies the surprising finding. For the empirical study on implications for pre-training data setting, we find that big synthesis small real is worth deeply researching. Pre-train with target classes first under limited computing resources. For the empirical study on the improved generalization of DA models, we find that real data pre-training with extra non-target classes, fine-grained target subclasses, or our synthesized data added for target classes helps DA. This paper also proposes a more large-scale synthetic to real benchmark for classification adaptation, termed S2RDA. It includes two harder and more challenging tasks, S2RDA 49 and S2RDA MS39. They contain more categories, more realistically synthesized source domain data coming for free, and more complicated target domain data collected from diverse real-world sources. We also provide a baseline performance analysis for representative DA approaches, and thus set a more practical and challenging benchmark for future DA research. Some future directions are listed here. This is a takeaway message, and please scan the QR code for our code and datasets. These are the references in the slides. That's all. Thank you.